Hey friends, reminder that in dark times is exactly when Christians have the most influence. When people are in darkness, when they're confused, they look for people who have answers, who have hope, who have joy. Just read of a priest in Italy who was on a ventilator and gave up the ventilator for someone else who needed it. The priest died. I think the other person is still alive. Reminds me of 2 Corinthians 4, 5, and 6. It's not ourselves that we proclaim. We proclaim Christ Jesus as Lord and ourselves as your servants for Jesus' sake. For the same God who said, "Out of darkness let light shine," has caused his light to shine within us, to give the light of revelation, the revelation of the glory of God in the face of Jesus Christ. Just pray during these times that when people look at Christians, they'll see Jesus. This lesson is on the first part of chapter 13, PowerPoint posted on Brightspace. And the two themes of chapter 13 are rigor and abstraction. This is happening in the 19th century, the 1800s. So this lesson is going to talk about rigor and then some early mathematicians who were involved in that effort. And then the second part later, we'll talk about abstraction. Let's describe an example of what we mean by mathematical rigor. So this homework problem was assigned. You were supposed to use Newton's method to find the tangent to x squared plus y squared equals 25 at the point 3, 4. So here's a circle, out here's 3, 4. We want the slope of this tangent line. So Newton would say, let's replace x by x plus x dot o and y by y plus y dot o. So x dot and y dot are derivatives and what we would call derivatives, and o is some small number. And so here's the algebra. And the idea is that we're moving away from the point x, y a little bit and still claiming that the equation of the circle holds at this new point. So some algebra to expand, then use the fact that x squared plus y squared equals 25. So the blue underlined terms cancel and we get here. And then Newton and a lot of the other people with similar methods said, okay, let's divide by O. So I can cancel an O out of each of these terms and get here. And now let's set O equal to 0 because it's really small anyway. So I get this, and finally solve for, in this case, y dot over x dot. We would write that as dy dx, and x dot is just 1. So when I do that, I get negative x over y equals negative 3/4. The slope of this tangent line is negative 3/4, and it all works. So people were happy doing that for a while, but there were some uneasy feelings, and it bubbled over in the 1800s. People started saying things like, well, at this stage, we were dividing by O. You can't divide by 0, so that means that O is not equal to 0. Then in the very next step, you're telling me that we're going to set O equal to 0. Well, which is it? Is O 0 equal to 0, or is it not equal to 0? And at this point, mathematicians just said, well, we can't answer that. It just works. So people started to look for why it works. First person to talk about, Carl Gauss, in the late 1700s, early 1800s, called the Prince of Mathematicians. So this is a big guy. He is almost universally agreed to be one of the greatest three mathematicians of all time. Those would be Archimedes, Newton, and Gauss. Just an interesting childhood anecdote. The legend at least has it that at age 10, Gauss's teacher asked the class to add up the integers from 1 to 100. And almost immediately, Gauss brought up his slate with the correct answer. The teacher thought this can't possibly be right, but it was. And this 10-year-old had immediately realized that there are lots of 101s in this sum. 1 plus 100 is 101, 2 plus 99 is 101, 3 plus 98 is 101, and so on. So in fact, there are 50 of these 101 terms, and so the way to compute it is 50 times 101. In fact, Gauss had just discovered this summation formula that we use a lot in discrete math, calculus, and so on. So, interesting anecdote, but to get into the serious things, at age 19, Gauss discovered that a regular polygon of 17 sides can be constructed with a compass and straight edge. Now, this is mind-boggling. People before this wouldn't have even thought about asking such a question. Of course, we know that equilateral triangles and squares and regular pentagons and hexagons can be constructed, and octagons and 16gons and so on, but 17 is a prime number. Where in the world did that come from? It turns out that Gauss's proof was entirely algebraic. He, in fact, didn't even do the construction. He proved that it can be done. Later, people actually succeeded in describing how to do the construction physically with a compass and straight edge. Gauss was very proud of this accomplishment. In fact, it was what convinced him to take up mathematics as his career. You may remember that Archimedes asked to have on his tombstone put the cylinder and sphere problem that he was so proud of. So Gauss on his tombstone asked to have a 17gon engraved. Here is Gauss's tombstone. There is no 17gon. The story is that the stonemason refused to carve it, saying that it would be too difficult and would just look like a circle anyway. Kind of sad. Some things about Gauss. He was a relatively private person, reluctant to publish his results even when they were revolutionary and groundbreaking. So this was the same thing that happened with Newton. Discover all of these things and then very reluctantly publish them, if at all, and then later there gets to be this dispute about who discovered what. Why didn't Gauss publish? Well, for one thing, he was a perfectionist, bar none. He was never interested in publishing things until they were perfect, and very few things ever are. He was also afraid, perhaps, of some controversy about some of his discoveries and fear of ridicule. In fact, he had children, but he didn't want his children to study mathematics. There's some speculation that he was afraid that they would weaken the family reputation, that he knew that they probably wouldn't be as good of mathematicians as he was, and he didn't want people thinking about the Gauss family as being mediocre. Many of his results were discovered later in his diary, which was not discovered until long after he died. So he was a famous mathematician during his lifetime, but even more so, people realized how gifted he was after he died, long after he died. He was arguably the last mathematician to be so-called good at everything. He contributed to almost every field of mathematics, and nobody does that today. People now today specialize in a tiny little corner of algebra or real analysis or something. Gauss was both a pure and an applied mathematician and even a scientist. So reminds me of Newton, actually. Gauss's proofs, though, were extraordinarily polished and precise, and he went to great pains to remove any hint of how he discovered these results. So we have this problem to this day. You pick up a paper or even a textbook, and here's this wonderful, elegant proof of a result, and how in the world did somebody discover this? It's just not mathematical style to usually write up the struggle and the ideas that went into the discovery. Here are some of Gauss's results. He gave the first rigorous proof of the so-called fundamental theorem of algebra. So this has to do with roots of polynomials. Well, here's a graph of a polynomial on the xy axis, and the places where the graph crosses the y-axis correspond to the roots of the polynomial. But not all polynomials have roots. So here's a parabola, 3x squared plus x plus 24, whose vertex is above the x-axis. And so this polynomial has no real roots. Gauss said, we want to flip over to the complex numbers, then every non-constant polynomial has a root. And it's important to keep in mind what complex numbers, real numbers, and imaginary numbers are. Real numbers are also complex numbers in this Venn diagram. Purely imaginary numbers are also complex numbers in this diagram. So when Gauss talks about having at least one complex root, if it turns out to be a real root, that's fine. That's included in what he's talking about. He was also one of the first people to start plotting complex numbers on an XY plane. So the real numbers go on the real part goes on the x-axis, the imaginary part goes on the y-axis. And now people could get a handle on what a complex number meant and what some of these properties that they were talking about, how they worked. So complex numbers soon became just as accepted as real numbers. Gauss was probably the first person to discover non-Euclidean geometry that we talked about in transitions. He didn't publish those results at all, and so he doesn't get credit for it, but in his diary and some of his correspondence, we realize that he probably did. It certainly did, actually. So things like hyperbolic triangles and so on, Gauss knew about. And Gauss was also very interested and gifted in describing the shape of surfaces, what today might be called part of differential geometry. So same figure here, this is a curved surface, but what do we mean by curvature? How can we measure curvature on a surface? Some other things that Gauss did. So some of you are in modeling right now. We talk about least squares regression, find a line that fits a set of data points. Gauss was the first person, or at least one of the first people to discover least squares regression. Again, didn't necessarily publish it, at least not right away. He was one of the first people to work with the normal distribution, which sometimes is called the Gaussian distribution after him. Wasn't the first person to study this curve, but one of the first person to realize that the errors, the differences of the points around the regression line tend to follow a bell curve. In linear algebra, he studied something called Gaussian elimination. Gauss shouldn't really get credit for that one, actually. The method was already known by Newton and others, but it became associated with his name. He should get credit for Gauss's law of electromagnetism. Lagrange earlier, and then Gauss improved discussion about how to relate electrical fields and electrical charges. So today, this is one of the founding or fundamental principles of electromagnetism. But Gauss's favorite and most important field was number theory. So he had this quote that mathematics is the queen of the sciences and number theory is the queen of mathematics. In other words, real scientists do math and the best scientists do math and the best mathematicians do number theory. So remember from transitions, this business about congruence, A congruent to B mod N, all of that is due to Gauss, and it greatly simplified people's calculations involving modulus, working with integers mod 7 or mod 12 or whatever. Back to Gauss's discovery that a 17-gon, regular 17-gon can be constructed. In fact, he did much, much more than that. He discovered exactly which regular n-gons are constructible and came up with a formula for the number of sides, and then you can just look at it and say, yep, that one is, and nope, that one isn't. And 17 happens to be one of them that are. Very ironic. The Greeks, remember, wanted to take algebra problems and convert them with rectangles and so on into geometry problems because they thought that geometry was the rigorous math and that you would use geometry to do algebra. Here now, Gauss is using algebra to do geometry, to answer questions about geometry. Moving on to someone called Fourier. Fourier's life work was to study the flow of heat in materials. So heat flows from hot to cold, and Fourier is trying to study what happens when you have this iron skillet or something and you put a fire under one corner of it. How does the heat flow through the skillet? His contribution was a series expansion, not this one. People already knew how to do polynomial expansion, which we call Taylor series. So to write a function as an infinite sum of polynomials, 1, x, x squared, x cubed, and so on. But a disadvantage of this is that the coefficients of this polynomial involve the derivatives of the function. And so the function has to have derivatives. In other words, geometrically, it has to be smooth. But scientists want to study functions that are not smooth. So back to this heating example, the skillet is sitting there and all of a sudden, almost instantaneously, somebody puts it over a hot fire and then pulls it off the hot fire and puts it back on and so on. And so that would be kind of like this red curve where a signal or a heat source is turning on and off. And this red graph has vertical transitions, and so it's not differentiable, and so a Taylor series doesn't work. Fourier's big idea, which is now called Fourier series, was to realize that instead of using polynomials to form a function, we could use an infinite sum of sines and cosines. And so on this, and in practice then, these are infinite series, but you cut them off after a while. Just take a finite number of terms to get a good approximation. So the black curve here is approximating the red graph that I want using just a few terms of the Fourier series. Another really important person, Cauchy. Their appearance is starting to get a little more normal. This guy could probably walk across IWU campus and not draw too much attention like some of our earlier people. Next to Leonhard Euler, one of the most prolific, maybe the second most prolific mathematician of all time, wrote hundreds and hundreds of papers in many different areas. And for our purposes, we're interested in rigor at the moment. So many of our analysis calculus proofs are stemming from ideas that Cauchy had. So you remember one of these tests for convergence of a series is the ratio test, where I take the limit of the next term over the previous one and see how big this number is. That's Cauchy's result. More importantly, he was the first person to really propose the idea of a limit. So people had been doing derivatives and integrals for 150 years or so. Now Cauchy is starting to say, well, there's this epsilon, and this delta, and they work together to describe what a derivative really is. He didn't get things in final form, but he was the first person to start this idea of what we mean by a limit, as well as the first person to think of the integral as the limit of a sum. So remember these approximating rectangles under a curve to approximate the area. Again, Cauchy didn't take this all the way like we have it today, but first person to think about doing this kind of thing. And last person, Galois. So he looks like a boy. The reason is that he almost was. Notice the short lifespan. He only lived 20 years. He was a political activist in college, expelled from his college for that. This was a very turbulent time in French politics, and even briefly went to prison for his political activism. He was killed in a duel. Apparently there was some sort of love affair between he and another guy over a lady, and he was challenged to a duel and thought he had to accept it. He lost the duel and died from a gunshot wound. But the night before the duel, he pulled an all-nighter, stayed up writing letters to his friends and mathematical colleagues in which he explained many of his mathematical ideas. Here's a page from one of them. You can just imagine this guy by candlelight frantically scrambling and scribbling out things that he had running around in his mind. It's a good idea for mathematics that he did, because otherwise those ideas would have died with him, but they survived. So what did he do? Mostly abstract algebra. if you've had abstract algebra, you've talked a lot about groups and finite fields and so on. If you haven't, just think of a group as being the integers where there's a set of numbers that you can add and they have negatives and there's a zero and so on. Also, Galois' theory of equations can then be used to prove that certain things are impossible. Galois himself didn't prove these things, but other people did using methods like he was discovering. And notice some old friends coming back. Galois' theory can be used and was used to prove that it's impossible with a compass and straight edge to trisect a general angle or to double a cube. And then later, Cardano and people like him were looking for a solution to a fifth degree equation with radicals. Galois' theory proves that that's impossible. And notice the irony here that, again, the Greeks thought that the real math was geometry, and if they had an algebra problem, they'd try to flip it over to geometry. Here are the two of the classical Greek problems that we now know to be impossible. They are geometry problems, but they are proven, the impossibility is proven using algebra. So by now, geometry is not king anymore, algebra is king. And we'll stop there.